Welcome students to the 8th lecture of Control System 2. So today we are going to discuss about the relation between state space representation and transfer function. So previously we have seen that for a dynamical system we can create infinite number of state space representation, but the transfer function is unique, means for a given system transfer function is unique, and out of that transfer function actually we can create infinite number of state space representation. So today we want to know that if a if a state space representation is given, then out of that how can we find out the transfer function. So as an introduction, that we are considering a conceptual model of a MIMO system where we are finding that m number of inputs are there, that is u1, u2, um. N number of state variables are there, that is x1, x2, xn, and the p number of outputs are there, y1, y2, yp. So the general model of a dynamical system is shown in figure 1. The time derivative of internal variable, that is xit, is used for the mathematical description of the system. That with the several examples we have seen that for a given dynamical system how to find the state space representation by finding the time derivative of the internal variable xit. For the linear time invariant system, which is our main focus for this course, that it will be possible in many cases to write the system equations in the following standard form. That is, x dot t is equal to a into xt plus b into ut, and yt equal to c into xt plus d into ut. Here A, B, C, D matrices have appropriate dimension. Y, U and X denote the output, input and state vector respectively. In general, the internal or state variable should be chosen to provide a complete description of the system. So that we have already understood that for a given system, if it is linear time invariant, then how to find out the state equation and the output equation. Now the question is how to find the transfer function from the state space realization. Means suppose a state space realization is given to you and you have to find out the transfer function from this state space realization. Then here one command is written which is ss to tf. Ss means state space, to tf, that is transfer function. In MATLAB there is a command called ss to tf, means if you provide to the MATLAB a, b, c, d matrices, and then if you use this ss to tf command, then the MATLAB is going to return you the corresponding transfer function. But here in this course we are going to know that what are the mathematical relation exist to compute the transfer function from the given state space realization. So now what will be the procedure to find out the transfer function from this state space realization. So now one thing you be clear that you see it is a set of differential. First equation, state equation, is a state of it is a state equation, and it is a set of differential equations. N number of differential equations are there, and now you know that the transfer function is an algebraic relation between the input and output. So definitely from the equation 1b you can see that the output equation algebraic in nature, but 1a is a set of differential equation. So how can I find out the algebraic relation from a given set of differential equation? So now the hint is that if you solve the differential equation 1a, set of differential equations 1a, then we can find the algebraic relation between the input and output. So that's why we will use the Laplace transform approach to find out the x of s, which is the we will find out x of s, which is the Laplace transform of the state variable from this set of differential equation. And second step, what we will do, we will substitute this xs in the 1b, means the Laplace transform of 1b, to get the relation between input and output. Let us do that one. So that's why you will find that immediately we have taken the Laplace transform of equation 1a. So how we will find out the Laplace transform of 1a? Now if you find the Laplace transform of ya, you can write in this way, that is x of s minus, sorry, it will be s into x of s, and minus, it will be x of 0 minus, because you know that once you will take the Laplace transform of a derivative term, so definitely there will be an initial condition will be equal to a into, because it is a constant matrix, so a into xs plus b into u of s. So from here we will find out what will be the xs equal to. Now this will be the expression of xs. Xs will be si minus a inverse x of 0 minus plus si minus a inverse b into us. So where I is the identity matrix, because you see S is the scalar operator, then if you want to do the subtraction from a scalar operator, that is subtraction of a n by, because what is the dimension of a is n by n. So if you want to do the subtraction from a scalar quantity, it is not possible. So with S, a identity matrix of n by n is multiplied to get the subtraction, and then we will find out the inversion of si minus a to write the expression of xs. So equation number 2 is showing the a state equation which is in an algebraic form, because when we will take the Laplace transform of a differential equation, then it will become a algebraic equation. So now here in the equation number 2, we can see the clearly two parts of the state equation in the frequency domain, one associated with the initial condition, which is symbolized at x0 of s, and another is associated with input term, which is xu of s. Now we will take the Laplace transform of the equation 1b. If you take the Laplace transform of equation 1b, it will be, here I am writing, it will be y of s is equal to c into x of s plus d into u of s. So this xs, us, ys are the Laplace transform of yt, xt and ut. So now already we got the expression of x of s. Now what we will do, we will substitute the expression of yx of s in the output equation, that is y of s, and we will get the equation number 3. Now from the definition of the transfer function, we know that it will be the ratio of output, Laplace transform of output to the input, assuming all initial conditions are 0. So if you look the output equation carefully, you will find that there are two separate terms exist, that is y0s plus y of us, and y0s is associated with the initial condition and yu of s is associated with the input. So according to the definition of the transfer function, we have to assuming all initial conditions are equal to 0. So definitely if we will assume that x of 0 minus is equal to 0, okay, don't be confused with this 0. It means that this 0 actually having a dimension of n cross 1 means all the initial condition of the states are 0. If you assume that, then we can make this equal to 0, and from there you can write that is y of s by u of s, that is actually the transfer function gs, is equal to c into si minus a inverse into b plus d. So this is a very important relation where you can see that if the a, b, c, d matrices are given for the state space, then with the relation 4 we can compute the transfer function of the system. Now, one important thing you can see that it is the transfer function matrix, because we are dealing with a MIMO system. So, whenever you are computing the transfer function for a MIMO system, then essentially the transfer function will be a transfer function matrix. So let us see that what will be the dimension of GS if we are dealing with a MIMO system. Then if we write the dimension, here, so what will be the dimension of Si minus A inverse? So dimension of A is n by n, and S into I is also n by n. So the subtraction results definitely a n by n matrix. What will be the dimension of B matrix? Because we have m number of inputs, so definitely the dimension will be n by m, the dimension of B. What will be the dimension of C matrix? We have p number of outputs, so definitely it having the dimension of p cross n. And what will be the dimension of D matrix? D matrix, there are p there are p inputs are there, and the dimension of this will be p by m. So now you're finding that ultimately the C Si minus A inverse into B, this results the dimension of a transfer function matrix, that is p by m. Fine. So now, if you are dealing with a CISO system, then definitely you are going to get a scalar transfer function. You are going to get a scalar transfer function. That is also evident if you write the dimension of the each matrices associated with the computation of GS. So in most of the cases you will find that D equal to 0. If you assume that D equal to 0, and you are dealing with a CISO system, then definitely you are going to arrive a scalar transfer function instead of transfer function matrix in case of MIMO system. So what for a CISO system, what will be the dimension of B? Definitely it is a n cross 1, that is a column vector. Si minus A inverse, it is n by n, and the dimension of C is a row vector, and it is 1 by n. So if you multiply all these quantities, the GS what you will get, that will be the dimension of 1 by 1, which in case of MIMO system GS you got, it will be the dimension of P cross M. Okay, so now you have to remember this formula to compute the transfer function GS, that is equal to C into Si minus A inverse into B. Fine. Now we will look about the total response of the system Y of S, what you got, to clear our further understanding. So just you look that Y of S, where you can see that it consists of two clear parts, that is Y0S and that is YU of S. Now if I want to compute the output of the system, that is Y of T, then we have to take the Laplace inverse of equation number 3. So now suppose that y of t, y0 of t is represented by Laplace inverse of y0 of s, and yu of t is defined as a Laplace inverse of yu of s. Then the total response of the system can be written, that is y0t plus y of ut, that is the sum of the zero input response y0t and the zero state response yut. So now from here again it will be clear that why the yut is named as zero state response. So let us see the expression once again of y of s. So now this y of 0s, we are calling it zero input response, because if you assume us is equal to 0, then only you will be left with y0 of s. So then it is clear that why the y0 of s is called zero input response. Now the yu of s is known as zero state response. Why? Because at that time, if you want to compute the zero state response, you have to assume the all initial conditions are equal to 0, and that's why we have named these variables for which the initial conditions are required to be known as a state variables, because that's why the name of this part has been given zero state response. Basically, the at time 0 are t equal to 0, for the state variables we are assuming that they are holding the value 0. So this is the reason why the y0 of s is named as zero state response. Now one important thing is there, that is the transfer function gs is a proper rational function with denominator, and denominator can be calculated as si minus a, the determinant of si minus a, and that will be a polynomial, and which will be the nth order polynomial, because we are dealing with a nth order system, and which is known as the characteristics polynomial of a. So now if we want to calculate the characteristics polynomial of a, then we have to find out the determinant of si minus a, and the solution of si minus a equal to 0 gives the eigenvalues of the matrix A. So if we know the A matrix, then by computing the determinant of Si minus A, we can compute the characteristics polynomial, and making it equal to 0 and finding out the solution of that polynomial equal to 0 will give you the eigenvalues of the matrix A. And another thing very important to note down, that this polynomial is the characteristics polynomial of the transfer function also. So from our previous knowledge, we know that if we will make the denominator of the transfer function is equal to 0, that will also give the pole location. Now the question is that, is the every eigenvalue of A is necessarily be a pole of a transfer function? Means, suppose if the A matrix is given, then by determinant of Si minus A, we can compute the eigenvalues of A, and using this formula C into Si minus A inverse into B, we can compute the transfer function from the state space representation. Now once you will find the transfer function, then it is the ratio of two polynomials, that is denominator and the numerator and denominator polynomial. And if you make the denominator polynomial, and that will be essentially in the form of 9 is equal to 0, then you will get the poles of the system. Now the question is that the every eigenvalue of A is necessarily be the poles of a transfer function. So answer of this question I will give little bit later, but before that we will come to know that how to use this equation number 6 to compute the transfer function. Then only probably this discussion will be clear what is the meaning of characteristics polynomial of A, and what will be the characteristics equation of a transfer function. That will be clear, we can visualize that. So the computation of transfer function from a state space, suppose one example is taken which is a third order system. So it is a 3 by 3, the dimension of a matrix is 3 by 3, and also it is a SISO system because the B matrix is 3 by 1 and the C matrix is 1 by 3. So definitely the transfer function what you will calculate will be the dimension is a scalar dimension. Okay, the dimension is 1 by 1. So now we know that to compute the GS, the formula of GS just we have defined, that is C into SI minus A inverse into B. So now first thing we have to compute that SI minus A inverse. So now first step, as a first step we are calculating that SI minus A inverse. So now SI minus A inverse is adjoint of SI minus A by determinant of SI minus A. That is the standard way to calculate the inverse of a matrix. So now SI minus A matrix has been calculated, which has been shown here, and if we want to compute the inverse of this matrix, then we have to calculate the adjoint of SI minus A. And how we will calculate the adjoint of SI minus A matrix? You have to find out the cofactors, and after finding the cofactors of this matrix, you have to take the transpose of that, and if you find the transpose, then you are going to get at the numerator matrix is this, and if you compute the determinant of SI minus A, you are going to get the polynomial, that is S cube plus A1 S square plus A2S plus A3. And our claim is that this SI minus A, if you make equal to 0, means S cube plus A1 S square plus A2S plus A3 is equal to 0, you can compute the eigenvalues of A, and this is known as characteristics equation of A, and it may be the characteristics equation of the transfer function also. So now to compute the final step, that is C into SI minus A plus B into D, okay, in this expression actually D matrix is there, though the value is not given, only D is given, so here plus D we have to write. So now if you compute the transfer function, then we are finding that the expression of the transfer function will look like this. And if you see the denominator of the transfer function, it is going to match with the characteristics polynomial of A. Means if you find out the eigenvalues of A matrix by equating is equal to 0, is equivalent to finding poles of the characteristics equation of the transfer function is equal to 0. Means for this case you are finding that definitely the eigenvalues of A will be same as the poles of the system, but it cannot be the case for the all kinds of realization that we are going to discuss now. Since the inverse of SI minus A can be expressed as a adjoint of SI minus A times the reciprocal of the determinant of SI minus A. So that is the formula of SI minus A inverse, adjoint of SI minus A times reciprocal of determinant of SI minus A. Since the adjoint of SI minus A has no poles, if you see the expression of adjoint of SI minus A, it does not consist of, it is in the denominator, sorry, it is in the numerator, so it is not going to consist any kind of pole. So it follows that the poles of this transfer function must be the determinant of SI minus A is equal to 0. That is the eigenvalues of A, what we have discussed now. That the eigenvalues of A by computing determinant of SI minus A is equivalent to make the the characteristics equation, that is s cube plus a1 s square plus a2s plus a3 equal to 0. So that's why has it follows that the poles of this transfer function must be the determinant of si minus a equal to 0. That is the eigenvalues of a. This is not to say that, this is a very important statement, this is not to, that is not to say that every eigenvalue of a is necessarily a pole. Unless further assumptions are made, there is no guarantee that some of the eigenvalues will not be cancelled out. So the cases can exist where that not necessarily the eigenvalues of a will be the pole of the system. Means if in a transfer function pole zero cancellations are there, then in that case you will find that the eigenvalues of a may differ from the poles of the system. We will discuss definitely this phenomena with an example in this lecture, but little bit we will discuss about this issue, that the additional assumptions which are required are the system should be both controllable and observable. Means you can guarantee that the eigenvalues of a and the poles of the systems will be same only when the realization what you have created, means the representation of the state space what you have created should be both controllable and observable. But at this point we are not knowing what is controllability and what is observability of the system. But at this moment I will tell you just to remember this fact, that the additional assumptions are required to guarantee that eigenvalue of a will be same as the pole of the system if the realization is both controllable and observable. So at this moment you will just remember this statement. Maybe we will discuss this issue when we will come to know what is the controllability and observability property of a state space realization. Equivalently, means both controllable and observable, equivalently you can say that system realization or representation is minimal. Means if a system representation is minimal, then we can equivalently say that system is controllable and observable, or vice versa. And also if a system representation is minimal or or both controllable and observable, it means that it has the lowest possible order of the characteristics equation for a given transfer function. So this fact actually we will verify today's lecture, that a minimal realization will be created from a transfer function if we have the lowest possible order of the characteristics equation for the given transfer function. We will definitely verify this fact. Now we will proceed that although there are many ways of representing system with a given transfer function in state variable form, it can be shown that all controllable and observable representation of a given transfer function are of same dimension. Maybe you can remember the last lecture where we have taken a RLC circuit where we have created different model, we have created 4 models from a given input output relation described by the differential equation. And once we are creating different model for a given given differential equation, we can assure that for that given differential equation always the transfer function will be same. So means from a given transfer function actually we have created 4 different models for that RLC circuit. And you can remember that the model 4 we found that it become a third order model, but the differential equation is second order. So at that time I told that it is good practice is that by looking only the A matrix we should not guess about the order of the system. Means here that thing is again stated in a different way. So when we are creating the different representation or realization from the transfer function, then for all the models have the same dimension only when if you guarantee that all the models are controllable and observable, both controllable and observable. Equivalently, all the realizations are minimal. So in a single input single output case, this is the degree of the denominator of the transfer function after common factors have been cancelled. Means you will get the dimension of a matrix will match with the degree of the denominator of the transfer function, that is the characteristics equation, only when if all the pole zero cancellations has been done. Only that cases you can guarantee that all the models out of that transfer function, means after the cancellation whatever the transfer function you will get, after the pole zero cancellation whatever the transfer function you will get, from there if you create the models you will find that for all the models the dimension will be same. We will definitely discuss this issue with an example again, that these things will be clear. If the output y and u are scalars related by 1, that is the state equation and the output equation, and if these equations are controllable and observable, that is the representation is minimal, then every eigenvalue of A is a pole of this C into Si minus A inverse into B plus D. So this fact definitely we will discuss, but time being we will not able to prove this, that if a state space representation is controllable and observable, then the every eigenvalue of A is the pole of the transfer function GS. That we cannot discuss, but definitely we will try to realize that if there is a pole zero cancellation, means at that time we will find that the system realization is not minimal. For that case we will see that the eigenvalues of A matrix are not same as the pole of GS. That fact definitely we will discuss, but when we will come to know about the controllability and observability, at that time we will come to again verify the fact which is stated by the last point. Okay, so that's why I have taken the same example what we have discussed in the last lecture, that RLC circuit, for which we have created 4 different model. So here you see this is the differential equation which is relating the input and output. Now if we are knowing the input output relation, then definitely we can find out the transfer function, that is from the differential equation 14 we can find out ys by s us is equal to 1 by lc s square plus 1 by rc into s plus 1 by lc. Now what will be the characteristics equation of this transfer function? Definitely the denominator polynomial is equal to 0. So this is the characteristics equation from the transfer function. And what are the poles of this system? The poles of the system can be calculated by making this polynomial is equal to 0, and these are the poles of the system. So this unique representation by transfer function we have found out. Now we have created different model from this transfer function, or equivalently we can say that from this differential equation. So we have created model 1 by assuming one set of state equation. Then we have created model 2 with assuming another set of state equation sorry, state variable. We have created model 3 by assuming by choosing another set of state variable, and ultimately we have the model 4 assuming the 3 state variable x1, x2 and x3. And especially the model 4 you are finding that though the we have the degree of the numerator polynomial of the transfer function is 2, but we got a model where the dimension of A matrix is 3 by 3. Okay, so we will treat this fourth model little bit separately, but first we will focus on the model 1, 2 and 3, because we are finding that for the model 1 the A matrix having dimension 2 by 2, which is matching with the degree of the polynomial of the transfer function, which is also 2, and also which is same for the model 3 and which is same for the model 2 also. Okay, so now any of the model we will choose and we will try to find out what will be the transfer function from that representation, and we will try to compute what will be the eigenvalues, whether they are same with the poles of the systems or transfer functions or not. That we will try to verify. So for that, what we have done, we have taken the model 3. Okay, so in case of model 3, we are finding that the state space representation is this is x dot equal to ax plus bu, y equal to cx plus du. So this is the A matrix, this is the B matrix, this is the C and D. So now we will proceed to calculate the transfer function as well as the characteristics polynomial of A to find out the eigenvalues of A matrix. So let us try to do that one. So now the transfer function is that G is equal to C into Si minus A inverse into B plus D. Here D is equal to 0. So we will compute Si minus A inverse, which is adjoint of Si minus A by determinant of Si minus A. So first we have calculated the characteristics polynomial of A, that is we are getting S square plus 1 by RCS plus 1 by LC, and if you make this equal to 0, we can calculate the eigenvalues of A, and by computing the eigenvalues of A, we are finding that they are same as the poles of the system, because we are finding that characteristics equation of the transfer function, that again I am showing characteristics equation of the transfer function and the expression to calculate the eigenvalues of A matrix are same. So that's why for this realization you are finding that the characteristics equation or the eigenvalues of A are same as the poles of the system. And let us calculate that the transfer function once again, that is C into Si minus A inverse into B. So adjoint of Si minus A has been calculated, then it is substituted in the expression of C into Si minus A inverse into B, and we are finding that we are going to have the same transfer function for which we have created the state space representation. So in this way, this fact is proved. That means it is very essential to understand that the realization what is represented by equation 21, it is actually the minimal realization. Means we can say that for the time being that it is controllable as well as observable. That's why the poles of the system is same as the eigenvalues of the matrix A. And also same time we have verified that even if the models are different way, it is created by assuming different state variables, but their input output relation is unique. That is, you will get GS equal to 1 by LC by S square plus 1 by RCS plus LC. I will request you to verify the fact with the model 1 as well as model 2, because for the model 1 and model 2 you will find that A matrix and B matrix and C matrix is given. You will verify whether you are getting the same transfer functions or not using the relation G is equal to C into Si minus A inverse into B. Fine. So now we will move to the model 4, because model 4 is little bit different, because here we are finding that degree of the polynomial of the transfer function which is created from this differential equation is not going to match with the dimension of the A matrix. Here the dimension of the A matrix is 3 by 3, and the polynomial of the characteristics polynomial of the transfer function is 2. Why it has happened? And now we want to calculate the transfer function from this 3 by 3 model, and let us see what will happen. So now we having a model 3 by 3, and this is 3 cross 1 and this is 1 cross 3. Now we will find out for this model 4 what will be the transfer function. So same way we will proceed. So before calculating the transfer function, we can calculate the eigenvalues of A matrix. So let us calculate the eigenvalues of A matrix by computing determinant of Si minus A. And you are finding that now the eigenvalues are 3 basically. So if you make equal to 0, one of the eigenvalue is 1 by minus 1 by RC, and another 2 eigenvalue we can calculate by computing S square plus 1 by RCS plus 1 by LC equal to 0. So you are finding that you are getting 3 eigenvalues here, but how many poles of the systems are? For this system, the poles are only 2. They are basically S1 and S2, this one. So now for this case, you are finding that the eigenvalues of A matrix are not necessarily be the poles of the system. And why it has happened? It has happened because the model what you have created from the transfer function is not minimal, and it can be verified later that the model is not controllable and observable. It means that there definitely a pole zero cancellations are there. So let us find the transfer function for this model. So now to compute the transfer function, we will go stepwise. We have to compute Si minus A. After the computation of Si minus A, we have computed adjoint of Si minus A, and then we have computed the Si minus A inverse by substituting adjoint of Si minus A by determinant of Si minus A, and then ultimately we have to compute the transfer function with the help of C into Si minus A inverse into B. And mind that now this is a matrix of 1 cross 3, and here you will get a 3 by 3 matrix, and this is actually 3 by 1. So if you multiply it, you will get a scalar transfer function. But you will find that while following the steps, if you see the second last step for the computation of GS, clearly you can see that there is a pole zero cancellation, that is S plus 1 by RC by S plus RC. So this is 1 0 is going to be cancelled out, and then you are going to get the original transfer function back, that is 1 by LC S square plus 1 by RCS plus 1 by LC. Okay, so one thing is very much clear is that if there is the pole zero cancellation, then what will happen, the degree of the polynomial of the transfer function may not match with the dimension of A matrix. It means that the eigenvalues of A matrix may not be the same as the eigenvalues of poles of the system. It may differ. It will be equal only when if you assure that the realization is minimal. What is the meaning of that? Minimal means the system representation must be controllable and observable. But we timing or not knowing the fact what is the meaning of controllability and observability. So definitely we are going to discuss that one when the time will come, and we will correlate this fact. But in this situation, it is very much clear that from a transfer function, infinite number of state space realization can be created. That is clear to us, because at least for the example what we have taken RLC circuit, we have seen that 4 models are created by assuming different state variables, though the transfer function for all the models are same. If output y and u are scalars related by 1, that is state equation, and if these equations are controllable and observable, though we don't know what is controllability and observability, but then only we can guarantee that eigenvalue of A is the pole of the transfer function GS. But even though we are not able to understand the controllable and observable, but one byproduct of this concept has been understood, that if a model is or realization is controllable and observable, there will be no pole zero cancellation. And if there is pole zero cancellation, then only you will find that there will be a mismatch between the eigenvalues of A matrix and the poles of the system. And also the dimension of the A matrix will differ from the degree of the characteristics polynomial of the transfer function. Now, amongst this infinite realization, are there any canonical or standard realization of a given dynamical system? You see, for a given transfer function, just now we come to know that we can create the infinite number of realizations. So out of that, is there any canonical standard realizations of a given dynamical system? Yes. Out of these infinite realizations, there are few realizations are there which are canonical, and that will be useful to analyze the system as well as synthesis of the controller design. So the next question is how to create this canonical standard realization of state space from a given transfer function, that is actually TF to SS. So in this lecture I have shown you that if a state space representation is given, then how with this formula we can calculate the transfer function. And now in the next class or next lecture, I am going to show you if a transfer function is given, out of that how can we create some of the standards or canonical realization which will be useful for the analysis of the system as well as for the synthesis of controller as well as observer design. And here one hint has been given, that is TF to SS. In MATLAB you will find that this command is there, TF to SS. If you provide the transfer function to the MATLAB with the help of the command TF to SS, the MATLAB is going to return you the state space representation, means it is going to return you the A, B, C and D matrices. But in the next class we will see that how mathematically we can create the canonical or standard realization from of state space from a given transfer function. Thank you.